Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Interesting experience for all of us, I guess. Okay, so it's my pleasure to introduce Vishal Monga from University of Texas, Austin. He's coming from the Signal Processing Laboratory in University of Texas. He's working with Brian Evans at UT, and today he's going to be talking on clustering algorithms in image hashing. So, welcome. Thanks for giving the talk, and please proceed.
Well, thanks much, Kibank, and I do really hope that there are people listening remotely to this talk. So thank you all who are paying attention to this. Thank you for inviting me here and giving me the opportunity to present my research. So as Kibank pointed out, I'm a PhD candidate looking to graduate soon at the University of Texas in the Department of Electrical and Computer Engineering. And the work that I'm going to be presenting today is a part of my doctoral thesis. And before I get started, I must acknowledge that my interest in this problem, or in fact the motivation for this work in particular, was born out of reading papers from researchers at MSR on image hashing, particularly Kibank, Venki, what was that, Tchaikovsky, and, and several other people. So I apologize if I did not get your name there. So here's a brief outline of my talk. I'll start off with a very quick introduction to the image hashing problem, the motivation for image hashing, applications, and then I'll give out formally the description of the properties of such a desired hash. And I'll be real quick on this part because I think a lot of people in Microsoft work on it and are intimately familiar with it, and a good number of people would have seen talks by researchers at MSR who have talked about the same problem. Next, I'll present my take on solving this problem, which is a two-stage hashing framework, where the first stage extracts visually significant features from the image, and the second stage involves compressing these features or clustering these features to a final hash value. Then I'll do a very quick review of the existing techniques in feature extraction. I'll not be exhaustive here, but the idea will be to categorize those schemes based on their philosophy. And more people coming, nice. The bulk of the talk will really focus on feature vector compression or clustering algorithms for feature vector compression. And I'll make my case first by arguing that conventional approaches for compression that are based on, say, vector quantization or an average distance type of cost are not really well suited for the hashing application. And I'll also do a quick reduction from a problem in graph theory to comment on the hardness of this problem. In particular, I'll show that it falls in the class of problems well known to computer scientists as NP-complete. And then I'll present polynomial-time heuristic algorithms for solving this problem. And finally, I'll single out the case of randomized clustering for special treatment to bring out the virtues of randomization for secure hashing. So a hash in all generality may be defined as a map from a set with an extremely large number of members to a set with a much smaller number of members, so a huge reduction in the alphabet. And hashes are used all over the place. And one question to ask straightforward is, why not use a traditional hash, a cryptographic one, or for that matter any other hash on multimedia data such as images? And I guess it's well known to the community inside of MSR that using such hashes is not really the right thing for multimedia data because they're very, very sensitive to the input or the data that's being hashed. And so that stems the need for robust perceptual image hashing, where the requirement is that despite the fact that images may be digitally different, if they have the same perceptual appeal, the hashes that should come from these images should be identical with a high probability. So perceptual here means based on the response of the human vision system in the ideal case, and robust means that under these small changes or small perturbations to the image, you should still get the same hash value. Applications of such a hash then lie in the area of image database search. For example, you want to look for an image in a database. Rather than doing an image comparison, you might compute hashes and compare them with pre-computed hashes of images in the database and search this image. There are also several other applications conceived in content-dependent key generation and synchronization in video watermarking, and folks at MSR have worked on those problems. From the perspective of this talk, though, I will focus largely on a robust image authentication kind of scenario, where the requirement is that the hash should tolerate incidental changes to the image or perceptually insignificant changes to an image, but yet be able to detect content changes. And here's what a quick example, a practical example of that kind of a requirement. In the center, you see an original TIFF image, a high-quality TIFF image of the former president and the first lady. To the left is a JPEG compressed version of the same image. And for all practical purposes, these two images look the same to the human eye. So it is desired that the hash values that come from these images also agree. And to the right is a tampered version of this image, where the face of the first lady is being replaced by that of a certain Monica Lewinsky. And therefore, it is desired that the hashes disagree.
Did you actually get a different hash value for that?
Yes. Right. OK, so here's a formal description of the properties, of the desired properties of such a hash. And people who worked here, Kimanch and Winky, are sitting right here. This formulation is very similar to the formulation that folks at MSR have developed. There's slight differences. And I'll start off by clearing up the notation. So the hash function takes two inputs. One is an image I, which I say belongs to a class of images. I'll denote this thing by a calligraphic I. And a secret key from a key space, which I will denote by calligraphic K. HIK then denotes simply the hash value extracted from that image using a specific secret key K. Then let I ident in I denote an image in the same family of images that is identical in appearance to Y. And let IDIF denote another image which is clearly distinct in appearance with respect to Y. And finally, let Q denote the length of hash in bits. A first desirable property is then that of perceptual robustness. And that is that as long as the images look the same to the human eye, it is desired that with a very high probability, the hash values agree. And likewise, there is a requirement of fragility to visually distinct inputs, so that images that are altogether different should result in hash values that have nothing to do with each other. And finally, for security applications, there is the all-important requirement of the hash being unpredictable. So what this property means is that without making any statistical assumptions on the source, which is the class of images here, it is desired that as the secret key is varied, we should get sufficiently uniformly distributed hash values. Before leaving the slide, I want to make a few important observations. First is my just made comment regarding security. So the last condition is definitely necessary but not sufficient for security. In particular, if you couple it with this one, you get a sufficiency criteria. Because what this condition means is not only that the images that are entirely different should map to different hash values, but this means is that it should also be very difficult to find an image IDIF, or in other words, to tamper with the content of the image I, especially as the secret key is varied, and yet get the same hash values. Second remark is, I guess, an obvious one, and that is that there is inherently a trade-off between these goals or these desired properties of the hash. And that is that there is obviously a trade-off between robustness and fragility. Depending on what content descriptors you use, you can either get a very robust hash, but then the fragility is compromised. So an example of a great robust hash is to have every image in the world mapped to the same hash value. And so you have a great robust hash, but obviously it's not fragile. So the kind of features that are used, kind of content descriptors that are used, facilitate this trade-off. And likewise, there is a trade-off between randomness and robustness, because randomness in general tends to improve fragility. So a good hash algorithm should not only try to achieve these goals, but facilitate trade-offs. A final important comment is that the manner in which these properties are laid out here might give the impression that the underlying probability spaces are the same, which is not the case either. In particular, for the first two properties, the probability space is all possible realizations of the hash algorithm over the product space I cross K, which is, when I say I cross K, I mean calligraphic I and calligraphic K. And the last, for the last property, the probability space really is, for a fixed image, all possible realizations of the hash algorithm as the key, secret key is varied. So,
do you have one quick question? Do you have an underlying probability distribution assumption on the images?
I will make that on the features that are extracted from the images later for the purposes of compression, but none for laying out these properties. Okay, so now we are into some PowerPoint special effects. So,
some fonts probably.
Right. All right, so here's my take on solving this problem. And what I propose to do is partition the problem into two phases. The first stage extracts visually robust feature vectors from the image. The second stage compresses or clusters similar feature vectors to a final hash value. And by a visually robust feature vector, what's meant is that feature vectors that are extracted from perceptually identical images, they should be closed in some notion of distance, whatever that notion of distance may be. And there are two motivations for this sort of an approach, really. First is that hashing quite naturally lends itself to be modeled as a clustering problem. In particular, the goal is to cluster visually indistinguishable images into the same cell. And secondly, this allows for a somewhat media-independent approach. For example, if you develop a common solution to stage 2 of the problem, a set of clustering algorithms that can work on features in an arbitrary space with an arbitrary notion of distance, then you can have a family of algorithms that can work across different media if you have an appropriate media-dependent feature extractor here. And this very much will be the focus of this talk. So I said this is the part that this talk is going to focus on. So prior to doing that, I'll very quickly review some of the very popular techniques in feature extraction. And before saying anything, I would say that definitely I'm not being exhaustive here. So I probably even missed out references from inside of Microsoft Research. So I apologize for that. But the idea here is to do sort of a coarse classification of the philosophy of the methods that have been proposed. So first family of methods is really based on image statistics. And the earliest methods in this category were based on looking at intensity statistics that divided the image into certain blocks and looked at either histograms or statistics like mean, variance, and higher moments of those blocks. And they found them to be somewhat invariant. But it is very easy to fool these family of methods. You can easily generate images that have the same intensity statistics, yet they may be perceptually different. And likewise, the other attack. So a scheme based on statistics of wavelet coefficients was proposed by Venkatesan et al. In 2000, ISO 2000. And in practice, it is seen that statistics of wavelet coefficients are far more robust than intensity statistics. Then there is another family of methods that is based on preserving coarse image representations. And the fundamental underlying principle here is that there exists a domain where you can project the image, or say a DCT domain or a wavelet domain, and very few coefficients can give you most of the information in the image. And so the typical thing to do is to either keep low frequency coefficients, or the equivalent of that in the wavelet domain is the low resolution coefficients, and quantize them and look at them as hash values. And most recently, there's also been an approach of looking at images as matrices and doing a singular value decomposition and keeping the strongest singular values in vectors. And finally, there is a class of methods that I will call as truly content-dependent methods. And the reason I call them truly content-dependent methods is because they really use the fact that this is an image. So they use the kind of things that eyes would look for in an image. So there are schemes based on feature point extraction, like edges and curves. And my own scheme for feature extraction actually lies in this category, which was presented at ICIP 2004. And in that case, I developed a basis family which explicitly tried to model the way eye perceives features in images. So I'll now move on to what is really the crux of the talk, which is a framework for compressing these features to a final hash value. So even before moving on to solutions for feature vector compression, let me put forward some goals and keep reminding them. The first is, of course, we want a significant reduction in dimensionality while retaining the desired hash properties like robustness, fragility, and there is the all-important goal of randomizing the hash. And a very hard question to answer here is what is really the minimum length of the hash value, the sort of an information theoretic question to meet these goals. So from the point of view of retaining the perceptual significance of the hash, this is really a quantitative description of that. And here let Li and Lj denote vectors in a metric space of feature vectors or in the feature space, which I address as V. And then it is desired that if they are close in, the vectors Li and Lj are close, then they should really map to the same cluster. And if they are greater than delta away, where the natural constraints 0 is less than epsilon is less than delta apply, then the clusters that these vectors map should be different. A rich perspective on this problem is to think of this as errors on the image. That is, all these perceptually significant attacks or perceptually significant, insignificant modifications can be thought of as errors, and you might want to compress while tolerating a certain amount of error. So a scheme for that has been proposed by researchers at MSR that give your feature vector or a binary feature vector as an input to an error correction decoding stage and give a significant, get a significant reduction in dimensionality. While this approach works fairly well in practice, there are two sort of philosophical deficiencies of the approach. And the first minor one is that it is only applicable to, say, binary feature vectors, but you can binarize other feature vectors, so that's not a very big concern. But the major concern is that the code book that is made available by error correction decoding is really a God-given code book. And what I mean by that is that that is not necessarily the best code book or the optimal code book for the hashing application. So more generally, we could think of this as a vector quantization. This is the terminology used in the signal processing community, or a clustering problem, where the idea is to do a partitioning of the space with codebook vectors ck, such that an average distortion less than epsilon in this case could be achieved. And the cost function here is an average distance sort of cost function, which is used all the time, and algorithms such as k-means and all are known for Euclidean spaces to minimize this kind of a cost. And in practice, such algorithms are not necessarily applied in the whole space, but on a subset of the space, which is known as the training set. So even with this sort of a cost, the question to ask is that it seems that the problem is solved. You can just do a traditional information theoretic compression and get a hash value, but there may be certain problems with this sort of a cost function. It might not be the best one, and here I put forward some arguments as to why that may be the case. First is that while if you do this kind of a minimization, you can get a guarantee, say, even if you find these codebook vectors, that the average distortion is less than epsilon, but you have no guarantee that feature vectors that are more than delta apart indeed map to different hash values. Or more generally, there is no straightforward way to trade off between these two goals. And again, this number of codebook vectors should be decided in advance. This is alluding to the same goal that you should know the hash length in advance. And so there is no, in this case, you have to decide on the number of codebook vectors and then do the design. And finally, there is a problem, say, with even the cost of the, rather the form of the cost that is in this expression, that there is a linear penalty for the errors that are made. Whereas in practice, you would really want to penalize some errors more strongly than the others. For example, if vectors that are really close and are not clustered together, or vectors that are very far away and are compressed to the same hash value, you want to associate different penalties. You want to associate really strong penalties with them. So what I propose to do is define an alternate cost function for feature vector compression or for hashing, and then subsequently develop a clustering algorithm that minimizes that cost. So here are the building blocks of such a cost function for hash compression. And I begin by defining joint cost matrices C1 and C2, and the particular entries of C1 are defined as an exponential cost, that is a parameter gamma and a parameter alpha here, raised to the power the distance between the feature vectors. So I say that this cost is assigned if the clustering algorithm makes an error of this kind, which is, let's call it an error of type 1, that if it was supposed to put things within epsilon together but it did not. And likewise associate a penalty, an exponential penalty, if an error of the second kind is made. And quite obviously in this case, the error should be a decreasing function of the distance. In this case, it should be an increasing function. That's why the difference in the sign of the exponent. And further define matrices that are very similar to C1 and C2, call them S1 and S2. And the difference is that the entries of S1 are defined to be non-zero exponential values for all such vectors that are within epsilon, as opposed to here, where they are defined non-zero value only if the clustering algorithm makes an error. And you might ask, what is the purpose of defining this sort of a matrix? And the purpose is to really normalize the entries in C1 and C2, and this is supposed to be C1 tilde and C2 tilde. So for folks that are using the right version of Windows XP, they get C1 tilde, others get to see what I get to see. So let's agree that this is C1 tilde and this is C2 tilde. So the idea is to normalize, because otherwise it's quite clear that this value is always between 0 and 1, while this one keeps on increasing. So you really want to be fair to both the components of the cost function. And finally, you can get your total cost function by taking an expected value of the sum of these matrices And to say that, I'll assume that we have an estimate of the probability distribution on the feature vectors available to us. So there are some things that are quite clear right here, which I pointed out when I pointed out the deficiencies of an average distance type of cost. First is there are clearly two terms in this cost. So there is, intuitively you can see right from here that there will be a way to trade off between these things. And secondly, of course, I argued that the form of the cost function in this case takes an exponential here, which associates a much larger penalty with vectors that are really close, or for errors on vectors that are really far away and get put into the same cluster. So this is a better cost function. And I also pointed out the fact that in an average distance BQ type approach, you have to first decide on the codebook vectors. So that the answer to that question will really come when I give out the clustering algorithm. So a natural question arises on the hardness of this clustering problem. And to be able to address this question, let's begin by asking ourselves that this particular question, which is the decision version of this clustering problem, that for a fixed number of clusters k, is there a clustering with a cost less than a constant? And to be able to answer this question, let's consider an analogous problem in graph theory, a pretty famous one known as the k-way weighted graph cut problem. So what you're given is a connected graph with a set of vertices v and set of edges e and weights defined on those edges. So that is, there is a weight on each edge eij. And the question to answer is that, is there a partitioning available of this graph such that the sum of these weights is less than a constant? Now, I'll not go through the details right now in the interest of the length of this talk, but it can be shown that by appropriately defining these weights and by appropriately making a graph, this problem can be reduced to our proposed clustering problem in log space. And this problem is well known that it is NP complete, so we make the deduction that the clustering problem that we are trying to solve here is also NP complete. So solutions to NP complete problems often rely on good heuristics.
But
So-
for the particular problem, that's very good approximation too.
Yes, so I'm trying to give a
Heuristic, I mean, provable good approximations.
provably good. This particular problem probably has.
Probably provably good approximations.
Yes, there should be provably good. I'll address that question towards the end of the talk. Okay. So solutions to such problems really rely on a good heuristic. So before just giving out the algorithm, I know I've delayed giving out the algorithm quite a bit. I'll just like to motivate my choice of the heuristic. And that is motivated by looking at another problem in computer science, or for that matter in combinatorial analysis, which is known as the stable roommate problem or the stable marriage problem. The one that I'm going to talk about is not the classical stable roommate or the classical stable marriage, but a variant of it. And the setting is the following, that given a certain number of rooms, it's useful to think of them as clusters, and people, it's useful to think of them as data points or feature vectors here. The problem is, how can you best group them so that the arrangement is stable? That is, in the ideal case, nobody complains, or at least if that is not possible, then the least number of people complain. And one of the known very popular ways to solve this problem is to give a preference to the bully, or the strongest guy, and let him make the choice, let him pick his roommates, and continue to do that in an ordered fashion. And intuitively, this minimizes the grief, because least number of people cry out. So as far as this clustering problem is concerned, the notion of strength or the bully is really captured by the probability mass that is associated with the data point or the feature vector. So with the analogy to the stable roommate problem in mind, I will now present the clustering algorithm to solve this problem. And the inputs to this problem will be epsilon and delta, meaningful notions. So these are positive quantities. A training set, which is a subset of this feature space. And we assume that we have both a distribution available on the features in the training set, as well as an ordering of them. So we start by selecting the data point associated with the highest probability mass, analogous to giving the preference to the bully. And then we make the first cluster by including all unclustered points, Lj, such that they are in an epsilon by 2 neighborhood of that. And I guess it would be clear to a lot of people what's the motivation for doing it. And if the notion of distance here satisfies triangle inequality, if this is a metric, then we know that within this cluster, the 2 points cannot be further away than epsilon. So subsequent clusters are made by continuing with this sort of a heuristic, but with an additional constraint. And let me explain this. I know this comes out from nowhere, so bear with me for a second. So subsequent clusters are made by looking for the next highest probability point or data point with the next highest probability, but we pose the additional constraint that the point should be at least 3 epsilon by 2 away. So if it is not, we go and look for the next highest probability data point that is at least 3 epsilon by 2 away. And what I mean by 3 epsilon by 2 away is in this notion of distance. So here you can see that I have defined the notion of distance for a point to a set. And the way we do that is simply by looking at the closest points. That is, look at that point and the point in the set that is closest to this point. So we assume that, say, a certain number of clusters are formed, and you want to look for a new data point which can serve as a candidate cluster center. So we do that by computing the distance of that point from all the clusters in this manner and checking to see if the minimum distance is greater than 3 epsilon by 2. And so we select the next highest data probability point which satisfies this constraint. And the motivation for doing 3 epsilon by 2, I'll just say that hang on, and I'll present the motivation in a minute. So assuming that we have such a data point selected, we again form the next cluster by simply making an epsilon by 2 ball or hypersphere around it, and continue to do so till no more clusters can be formed. So now let me give you quickly the motivation for that. I'll do so by visualizing the clustering algorithm that I just gave out. And before doing so, I want to make the point that this is by no means representative of the true geometry of the situation. This is just for an aid in conceptual understanding. I mean, this is not a Euclidean space or such a regular lattice space. So let's say we start with the highest probability data point and make a epsilon by 2 hypersphere around it. And again, depending on the geometry of the space, it can be anything. It doesn't have to be circular. Now, the motivation for choosing the next cluster center 3 epsilon by 2 away should now be clear, that if you do that, you know that this point to this point is 3 epsilon by 2. So the maximum distance between the closest points in any two clusters can be epsilon. So you know that you're not making the error of putting together points that are greater than epsilon away into the same cluster. So it is basically to avoid that. And subsequently, all clusters can be made in the same manner. You look for the next highest probability data point and make sure that the distance between any two clusters is always greater than epsilon. So that was the motivation of looking for the next point at least 3 epsilon by 2 away. So let me summarize the clustering algorithm. Another thing that you might see here, which is actually quite obvious, is that the whole space is not filled. A lot of data points are still left unclustered. You can only make a certain number of clusters by going on in this fashion. So I will give out approaches to address the remaining data points shortly. But let me make some observations of what I had described as the basic clustering algorithm. So first one is a repeat of what I said earlier, that within any cluster, the distance between any two data points is at most epsilon. And the reason for that was based on the assumption that the notion of distance on these feature vectors should satisfy triangle inequality. And that's a very reasonable assumption to make in practice. And another very important thing, which kind of summarizes why the basic clustering algorithm came out the way it was that by continuing in this manner, we made no errors until this stage of the algorithm. So I just pointed out that there are no errors of type 1 because we made sure that each of the clusters was greater than epsilon away. So the minimum distance between any 2 points was at most epsilon. So you could not make any errors of type 1 or the kind of errors that if things are less than epsilon away, you put them in different clusters. And also, you did not make any errors of type 2 because within any cluster, again, the distance between any 2 points is epsilon, which means it is less than delta because of the natural constraints. And hence, it never happens that things that are greater than delta apart map to the same cluster. And of course, since you can no longer continue in this fashion, you know that the data points that are left unclustered are at least 3 epsilon by 2 away from each of the existing clusters. So I'll next present 2 approaches to handle the unclustered data points. So before giving out the approaches, let me quickly summarize what these approaches do. So the first approach is based on guaranteeing that the expected value of C2 tilde is 0. That is, there are absolutely no errors made by putting things that are greater than delta away into the same cluster. And so essentially the intuition here is minimize the expected value of C1 tilde exclusively, conditioned on the fact that the expected value of C2 tilde is 0. The second approach is the one that exploits the structure of the cost function, that there are 2 additive terms, so it can trade off the minimization by appropriately weighting each of the terms. So with that in mind, I'll first give out my first approach to handling the unclustered data points. So as before, we start with the point that has the highest probability mass amongst all the data points that are left. And for each existing cluster, we compute this quantity. So this quantity is again the notion of the distance from a point to a set, but now this distance is defined differently. That is, we now look at the points in the sets that are the furthest away from this point rather than the closest one. And so we compute this quantity for each of the existing clusters. So what we're really trying to do is we have this point L star, and we are trying to decide what to do with this point. Give it to one of these clusters or do something else. So then we compute this quantity S of delta is equal to Si such that Di is less than delta. That is, we look at all the clusters for which this distance is less than delta. If we cannot find any such cluster, then we simply open a new cluster with this as a cluster center. If we can find one or more than one in general clusters in this manner, what we do is we compute this expected value of C1 tilde type error. And this is really computed over the complement of the cluster that we are considering assigning to. And I know this is convoluted language. And what this means is that if you consider assigning it to cluster Si, then you should really look at the cost over all the other clusters. And there is no expected value of C2 tilde type term here in the cost. And that is because of this particular reason, that you are only looking at clusters for which this distance is less than delta. So you know that you cannot make any errors of that type. So finally, we simply look for the cluster for which this cost is minimum or consider assigning it to the guy for which the least of the other guys cry out. And we continue to do this until all the data points are exhausted. Approach 2 then again starts with the same heuristic that has been underlying throughout. That is, look for the data point with the highest probability mass. But unlike approach 1, there is no constraint imposed. We consider all the clusters and compute a joint cost and weight them by a parameter beta. And basically, beta is used to trade off expected value C1 tilde versus expected value C2 tilde. And essentially, based on the value of beta, you get, so the beta is equal to half then results in the original cost function, or a joint minimization, and beta is equal to 1 results in an exclusive minimization of the expected value of C1 tilde type cost. So in this case, there is no constraint imposed, and we simply look at an instance of this cost function for a value of beta, and then look for the cluster for which this cost is minimum and assign the data point to this cluster. And again, you continue with these steps till all the data points are exhausted. So let me now do a summary of all the detail that has been going around. So approach 1 really tries to minimize expected value of C1 tilde condition on expected value of C2 tilde is equal to 0. And what this means is that this never happens that feature vectors that are greater than delta apart map to the same cluster. And a question that can come to the mind is why not have a dual of this approach? That is, try to minimize expected value or make expected value of C1 tilde is equal to 0. Try to minimize expected value of C2 tilde condition that expected value of C1 tilde is 0. And a little bit of thought, it will become clear that that really accounts for absurd clustering algorithms, because again, the only way you can make this thing completely 0 is by mapping everything into the same cluster. So there is no meaningful dual of approach 1. Approach 2 then, as I said before, smoothly trades off the minimization of this versus this. I'll shortly present some results showing the kind of cost function values that you get. And beta is equal to half corresponds to a joint minimization, while beta is equal to 1 corresponds to an exclusive minimization of this particular component of the cost function. And two very nice properties that probably got camouflaged in all the detail is the following. One is the clustering algorithm terminates really naturally with a certain number of clusters. So the final hash length given by a ceiling of the log of the number of clusters that is formed is determined automatically. So this was a problem with say using traditional approaches for compression, where you start with a number of codebook vectors and try to compress. Another really nice thing is that at no stage in the algorithm did I make use of any other fact except that the notion of distance on these features satisfies triangle inequality. So this could work on features defined in any vector space, Euclidean, Hamming, Hausdorff, etc.
In principle, if I allow to use more bits, if I allow the usage of more clusters, then I should be able to decrease the cost function, right? So that doesn't really come into the picture of the algorithm. Is that somehow linked to the choice of epsilon and delta in the choice of the C1 and C2?
Right. So That's correct. It is, I mean, the number of clusters are directly a function of epsilon and delta. And if you want to do so by using a more number of bits, or in fact even less number of bits, then you can develop a variant of this clustering algorithm with a fixed number of clusters, which means you can decide on the number of clusters, continue with the assumed heuristic, execute it in the same manner, but get the number of clusters that you want. So you can really use this as a reasonable guess to begin with for the number of bits that your hash value should have.
So did you try that? I mean, so suppose you want to design your hash function such that in the end you want to get it, let's say, 256 bits, period. So did you do sort of like an iterative technique in order to
Well,
achieve
I didn't try that.
Okay.
Yeah. And so here are some results of what I should call now as the deterministic clustering algorithm, because there was no randomization in there. Shortly I'll talk about randomized clustering, which I believe is the interesting part of this talk. And the problem that was addressed was trying to compress a binary feature vector of length 240 bits. And the notion of distance that was used was normalized Hamming distance with the epsilon 0.2 and delta 0.3. And the table here shows a comparison of the clustering algorithms that are just proposed with the, say, error correction decoding or an average distance VQ type approach. And what you're trying to see here is the values here are the value of the cost function that is achieved by each of the clustering algorithm. So first thing to do is compare the cost in these 3 rows with the cost in these 2 rows. And what you see is that even at the same rate, that is with approximately the same number of bits, in fact, a little bit an advantage here, you get much lower values of the cost function here. And this re-emphasizes the story that the code book by error correction decoding may not be the best code book. And within these 3 rows, you can look at the kind of trade-offs that I talked about earlier. And that is that approach 1 gives you a slightly higher cost for expected value of C1 tilde, but it guarantees that this guy is 0. And approach 2, when used with different values of beta, allows you to trade off between a joint minimization versus an exclusive minimization of expected value of C1 tilde. So here is a more qualitative feel of the cost, that you might say that, okay, I look at this value of the cost function, but what does it mean? I mean, what happens in practice when you apply this hash algorithm? So here are some results for that. So I applied a feature vector that I did not present in this talk, but a feature extraction technique based on end-stop wavelets based on a modeling of the visual system. And the 2-stage hash algorithm was applied to a natural image database of 100 images. For each image, I generated 20 perceptually identical images, and using standard benchmarks. So the typical attacks included the ones that are seen in this community, like compress the image with a reasonable quality factor such that the perceptual quality is not lost, add some noise to it, and small geometric attacks of rotation and cropping and linear nonlinear filtering. And the result was that the final hash values for the original and distorted images were same in over 95% of the cases. And in all, I got to see only one collision in all possible pairings, which is 100 choose 2, 4,950. I have a qualitative comparison with the VQ and error correction decoding also on how they do, but my preference would be to come back to it later in the talk. I have it as a backup slide. I say more analysis here because I really want to talk about the randomized clustering part of the story right now. So I'll now try to present a randomized clustering algorithm. And to begin with, let's recall that the heuristic for the deterministic map or the deterministic clustering was selecting the highest probability data point as the cluster center. And we kept on repeatedly following this heuristic, respecting the heuristic that the stable roommate problem gives us. And so to randomize this, we look at the statement in this manner, that we select the highest probability data point as the cluster center with probability 1. So if you want to randomize, you do so you choose cluster centers in a probabilistic manner. And within this algorithm, I do so by introducing a new randomization parameter S. And what I do is I compute a new probability mass function in this manner. So this is pi to the power s, where I denotes the ith data point. So to understand what's going on here, let's quickly look at an example. So let's say a very, very hypothetical situation where we have, say, 4 data points with these probabilities. And if we choose s is equal to 1, what happens? So if there was no randomization, if this was a deterministic map, then we would simply go and pick this guy as the cluster center. But in this case, what we do is we generate a uniform number. So the probability that the uniform number is going to fall in the range 0 to 0.5 is 0.5. So we go ahead and pick this value with its own probability as the cluster center. So this is for the particular choice of S is equal to 1. And what I'm showing here is nothing very special, but the classical approach of taking a uniform random variable to any distribution that you want. So more generally, the role of S can be understood as following. As S tends to 0, this new distribution that is being introduced, pi I of S in the previous slide, really tends to a uniform distribution, which means that any point is selected as a cluster center with the same probability. And as S tends to infinity, I should really be saying tends to infinity rather than equal to infinity, I hit the deterministic clustering algorithm. So take the limit of this expression as S tends to infinity. And so this evaluates to 1 for the data point with the highest probability and 0 otherwise. So I'll now present some experimental findings that I did that bring about the virtues of this sort of a randomization. And once again, the conjecture, the underlying conjecture would be that randomization makes the job of generating malicious inputs significantly harder. Or for an adversary to generate images that he tampers with the content of an image and still gets the same hash value, you want this sort of thing to not happen. So before presenting these results, let me introduce the last round of notations in this slide. So let U denote here all possible feature vector pairs in L, the training set over which the clustering algorithm was performed. And let E, a subset of U, be the error set for deterministic clustering. What I mean by the error set is the set over which the deterministic clustering makes errors. The model for an adversary is really a qualitative one, but nevertheless with a lot of advantage given to the adversary. And that is that the adversary has complete knowledge of the feature extraction as well as the deterministic clustering. And so obviously what he will try to do is he will contrive to generate input pairs over the set E so that he can get errors. And one important point that I want to make here is that in general, the motivation for randomization comes from the fact that no matter what content descriptor you use, content descriptors are likely to fail, features are likely to fail. They will not always do your job perfectly. So what you want is to make the problem harder by means of randomization. And now I'll see how that happens. So here's the first plot which explains almost most of the story. And what I'm showing here is a plot of the cost function value versus decreasing values of S from the deterministic case, which is S equal to infinity, and as S tends to 0. So this cost here, something around 7 into 10 to the power minus 9, is the kind of cost values that I showed you in the table when I presented results for deterministic clustering. And this cost is being showed over the set E. So for the deterministic clustering, this is the set which has all the error. So all the cost is here. And what is seen here is that as randomization is increased beyond a certain level, the adversary meets with very little success over generating, by generating inputs over the set E. So what this shows is that when you go sufficiently further in S, in this particular experiment, for values of S less than 1,000, the adversary really has nothing much to gain by generating input pairs over this set. You might say that, okay, this sounds nice, this sounds good, that over the set E this happens, but what about the rest of the space? What happens in U minus E? And so here's the rest of the story. So this is a similar plot, I mean the cost function value versus decreasing values of S over the set E bar, or the complement of the error set, or U minus E, in other words. And obviously for the deterministic clustering case, there were no errors over this set. And what you see is that the error gradually increases as we would expect, and goes to a fairly high, not so likable value. But a far more illuminating discovery is made when you look at the cost over the total set, that is the set U is equal to E union E bar. And what you see here is that there is a range of S, say from 1,000 to 40 here. Now these are coarse numbers, I did not put down the exact numbers. And what you see is that by using values of S in this range, you get about the same values of the cost function which are likable for your clustering algorithm to retain the perceptual significance of the hash. And at the same time, you have significantly enhanced the security, because if you go back and look at this, then for values of S less than 1,000, the adversary had very little success by generating inputs over the set E. So an appropriate choice of S can be made that gives you very high security while largely preserving your robustness properties.
So intuitively, what's
What's the reason why we don't see a monotonic behavior here in S?
That's actually a very, very good question. And when somebody says it's a good question, you don't have a perfect answer. But let me give you an answer that should intuitively suffice, may not suffice quantitatively perfectly. And that is that, yes, on a global level, you should see an increase in the values of S. But what happens in local neighborhoods is really an outcome of the clustering algorithm. It's just based on that. You cannot, the clustering algorithm, I mean, analysis needs to be done to see if there is really a constraint that obviously the errors, the results show that there is definitely no such constraint, but that is pretty much the reason. So this is just the plot here bloated in this range 100 to 40. So what I'm trying to show is the numbers here are within 10 to the minus 9, which are likable quantities. And in general, if you want to enhance security, then you may even pick your S pseudo-randomly.
That may be important because for a given data set, you don't know the value of S.
Right. So yes, that's correct. For a given data set, you may not know the value of S. Depends on the. So final comment on the uniformity of hash values. That was the third desirable property. And what I'm trying to show here again is the well-known Kullback-Leber distance in information theory. And this particular plot shows for a typical image in the experiments, a Kullback-Leber distance of the distribution of the hash that we get by varying the secret key versus ideal uniform distribution over those set of hash values. And again, what you can see is that as S goes to our likable range of less than 1,000, you get roughly uniformly distributed hash values. It's not perfectly uniform. So in conclusion, what I...
So how come, to go back to the previous slide, so how come, why is the uniformity increasing as you increase S, as you introduce more randomization?
Well, that's because the cluster centers are assigned almost randomly. And that's what determines how uniformly, yeah.
The clusters are originally chosen by randomness. They go,
Yeah.
centers, they go very close to each other.
Correct. Thank you. So here's a conclusion. That what I proposed was a two-stage framework for image hashing with a media-dependent feature extraction followed by almost media-independent clustering. The reason I say almost media-independent is because really the features that you get, the notion of distance that you get and even the distribution that you get that you need to use in your clustering comes from the features or the feature space. But nevertheless, the good thing is that you can still do it for arbitrary notions of distances. And as a solution to this problem, which I showed a reduction from a graph theory problem to be NP complete, I proposed heuristic clustering algorithms where a greedy heuristic was employed. Randomized versions of that clustering was shown to reduce vulnerability to malicious attacks, and trade-offs between the goals of the hash algorithm were facilitated. There are two problems of interest that are of great interest to me, and I just learned that it's also of interest to Venki. So he just asked the question that, can you say something about how good your heuristic is? And this is the kind of stuff that people who really deal with clustering algorithms in theory are really concerned about, and that is that can you find out the number alpha such that this really lies within alpha of your optimum cost? And from the perspective of hashing, I think it's valuable because if you can do something like this, then you can really probably give some upper bounds on the theta 1s and the theta 2s that I showed in the second or third slide, where theta 1 was really trying to tell you with how high a probability did you match. Another problem that is of great interest to me, and my hope is to be able to put this in my dissertation, furnish a formal proof of this, and this is probably not that hard. The I here, I'm sorry for so much notation, is the mutual information in information theory, and here I'm really looking at the image as a random variable and the hash value also as a random variable, and what we're trying to see is that as your randomization stretches to the extreme, what should happen is that this mutual information should go to 0, or in other words, the hash should not leak any information about the image that it's being computed from. And literature on this work are these set of papers right here, and with that I pretty much conclude my talk. Thank you for paying attention for members here and those listening to it remotely, and if there are any further questions, then I'll try my best to answer them. I'm sorry, I'm coughing.
I actually have one question. So one more question. So
Okay.
the results you presented are based on the training set. So did you ever do an experiment where, let's say, you do the clustering on a training set and then, you know?
Actually, the results here are not on the training set because in the case of a Hamming space, there are only finite number of them. So you can take the whole thing and do it. But yes, if you are talking about a space where there are infinite number of vectors, then you have to do it on a training. So this
Infinite is same as exponentially. The 2 to the 60 vectors you can.
Yeah. So it was actually done by, so there are two ways to do it. One is really do it on a training set, and for the earlier half of the results that I showed in comparison to error correction decoding, for error correction decoding, what you did was you took basically segments of your complete intermediate hash and brought them down. So that's what I did also, just to get a fair comparison between the two approaches. But the answer to your question is I have to do it.
Thanks.
Thanks.
I'll see you later.
Okay, actually you can be here. So this is the ROC. So